Assalamualaikum warahmatullahi wabarakatuh. So this is the last subtopic in the AC power. AC power. Okay, so unbalanced three-phase load and the power calculation. So the learning outcome. So we have four. So the first one, after the completion of this lesson, the student should able to differentiate between what you call balanced and unbalanced condition. The second one, you are able to calculate the three-phase AC power system using phase, line voltage, and phase and line current. Analyze simple and complex three-phase problem. And the last one, know the method to calculate or to actually measure AC power using wattmeter. So unbalanced three-phase load. So what is the definition? Is actually the impedance in one or more phases. Phases differ from the impedance of other phases is said to be unbalanced load. So meaning that if your ZA is different compared to ZB and ZC, meaning that this load is unbalanced and the whole system is actually in unbalanced conditions. So if you have unbalanced system, so we cannot apply the relationship between line voltage and phase voltage that we have previously learned okay, in the balanced system. So actually the relationship between line voltage and phase voltage can only be applied if the system is balanced. So to get the line voltage, okay, for example, we have already know VAN. This is actually V phase, VAN, VBN, and VCN, while for the V line, is actually VAB, VBC, and VCA. Okay, so to calculate VAB, for example, the V line, so what you need to do is to manually calculate VAN. Okay, sorry. Oh, sorry. Okay, sorry. So this one VAB, for example, so you need to calculate manually from VAN minus VBN, and to get VAB and then also VBC. Okay, so VBC is VBN minus VCN, and the last one is VCA. You can calculate by using VCN minus VAN. Okay, and to get the line current IA, so you need to calculate by using this one, this equation, IB and IC. And as you know that usually for the star connection, we usually come with what I call the neutral cable, and the neutral cable line here you can calculate is equal to negative IA plus IB plus IC. And for this unbalanced system, you have IN has a value, okay? Because this is the unbalanced current will actually flow through inside the neutral cable. So this is for the Y connection. So I would like to highlight again that we cannot apply the relationship between line voltage and phase voltage. So you need to use this equation to calculate the parameters. Together with the delta, okay, so as you can see, when the load is connected in delta and you as been see here, the load is unbalanced, okay, so you need to actually calculate the line current, line voltage, phase current, phase voltage and phase current manually by using this equation. For example, to calculate the IAB, which is this one, this is actually the current that flowed from A to B, VBC, IBC, and this one is ICA. So to calculate IAB, so you need to calculate this one is VAB over ZA, and for the delta connection, V line is actually V phase. Okay, and then from this equation also, as you can see, to calculate the line current, you need to use this equation also. Okay, so for IAB, so it is actually IAB minus ICA. IB is IB minus IAB, and for IC is ICA minus IBC. So example one, so given an unbalanced delta connected load, which is ZAB is equal to this one, ZBC and ZCA, supply voltage is 110 volt. So this one is not mentioned whether it is line or phase or RMS. So usually, so this one is already been given. This is actually V phase, okay? V phase, but I assume that this is V RMS. And it is a positive sequence and VAB as a reference. So calculate the phase current, the phase and line current, and construct the phasor diagram. So I'm using Microsoft Whiteboard. Okay, so this is delta connected. So okay, sorry, too big here. So I'm going to use this one, I think. Okay, so we have this one, A. Then you have your seg A. This one is a AB, okay. Seg, then we have this one. So this one I put as a B, this one as a C. So this one is a AB, ZAC, sorry, ZCA, okay. ZCA, and this one ZBC, okay. And we know that this point, this voltage is VAB, okay. So, and we know that for delta, V line is V phase. Okay, so given the, for example, we want to get, we have been given an impedance, ZAB, ZBC, and ZCA. Okay, meaning that the current that we obtain will actually, this one is VAB minus over ZAB is actually a current of IAB, which is this one is I phase, okay? So this one 110, and then we use the ZAB, VAB as a reference, so meaning that this one angle 0, okay? And the ZAB is 6 plus J8. So we can calculate the value, which is the value IAB is 11 negative, the way angle of negative 53.13 degrees. Okay, and IBC, so this is IAB, IBC, and ICA. So this one is actually VBC and then ZBC. And VBC, so the magnitude is the same, 110. Okay, and since it's a positive sequence, meaning that the angle is negative 120 degrees from the VAB. Okay, so 4 minus J3. So we can calculate the value is 22 ampere with an angle of negative 833.13 degrees. Okay, and ICA is VCA over ZCA. So CA, so 110 positive 120 degrees. ZCA is 8 plus J6. So this one, by using calculator, the value is 11 ampere with an angle of 83.13 degrees. So this is all ampere in RMS because the voltage is already in RMS. Okay, so this is the phase current that we have obtained. So this is I phase. Okay, and how to get the line current, sorry, line current. So actually the line current is IA. So this one is IA, IB, and IC. So based on the KCL here, you can actually obtain that IA is actually equal to, okay, so IA is equal to IAB minus ICA. IB, okay, IB is equal to IBC minus IAB, and IC is equal to I CA minus IBC. So this is all I line. Okay, so you substitute the value here. IAB, you have already obtained 11, negative 53.13 minus the ICA, which is 1183.13, and for IB is actually IBC 22, negative 83.13. Okay, minus ICB, sorry, IAB, okay, this is IAB, which is 11, negative 53.13, and IC is ICA, 11, 83.13 degrees, minus IBC, 22, angle negative 83.13. Okay, so that's all for example 1. So I hope you can continue on solving this. Okay, so this one, example 2, we will actually discuss. Okay, I will maybe we'll do some the solution, and then you may refer to the solution. And also example 3 and example 4. Okay, so this is the Y connection, which is we have already discussed. Usually they will come with the what we call the three-phase 4Y system, where we have the neutral cable here. So what happens when the neutral cable is disconnected, or sometimes actually malfunction? So how to analyze this circuit? Because if you don't have the neutral cable here, neutral line here, so you cannot actually calculate the VAN here. Okay, VAN is no longer valid. Okay, so but do not panic, because it actually simplify the circuit calculation, okay, or the analysis. So if the neutral line is disconnected, the analysis can be done by using a very simple mesh current analysis. Okay, so as you can see here, you need to draw the line mesh current here. So we have two mesh current here, I1 and I2. So from here, you can actually calculate the IA, DVAN, VAB, and so on. Okay, so the what we call the best solution is by using mesh analysis. And also, if you don't very familiar with the mesh analysis, so you can do the what I call the Y to delta transformation to solve the problem. Okay, and then this is example 5. So we will discuss also during the class, or I also will make the solution, okay, in a Word file and so on. Okay, so power in a balance system. So we go back to the balance system. So how to calculate the power in a balance system? So in a three-phase balance system, so the total power of the system is simply just summation of all phases. So P1, P2 plus P3 for the real power, And for the reactive power is also the summation of the phase 1, phase 2, and phase 3 reactive power. Okay, where the P is V phase, I phase, cause the different angle between the phase voltage and the phase current of that respective phase. And Q is V phase, I phase, sine theta V phase minus theta I phase. Okay, and so meaning that if this is the summation, so if the system is balanced, so meaning that the P total is just a multiplication of 3 multiplied with the single phase power. Okay, so in other words, so the 3-phase power system can be calculated by using 3 multiplied with the single phase power. Okay, so this is actually, as you can see, is actually in phase term. Okay, V phase and I phase term. If you are using V line and I line term, so the P total can be actually calculated using this equation: square root 3 V line I line cos theta V minus theta I 1. Okay, and the same case goes to also for the reactive power. So the total reactive power is just 3 multiplied with the V phase I phase sine theta V minus theta I. But if you are using V line and I line, so you need to multiply with the square root 3. Okay, and for the apparent power, so you need to multiply also. Just simply multiply 3 V phase I phase, and the unit is VA. Or in other words, if you are using V line and I line, so the total 3-phase system power is actually square root 3. And for the complex power, so 3 multiplied with V phase, I phase conjugate. So if this V3, V phase, I phase, and square root 3 V line, I line can be applied both in delta or Y connection. Okay, let's prove it. Okay, we already know that for active power, for three-phase active power, you can actually, the equation is 3 multiply with the V phase, I phase cos theta V phase minus theta I phase. Okay. Okay, so let's see when the load is actually in what we call Y connection. Okay. And for Y connection, you should know that, oh sorry, for delta connection, you should know that V phase is equal to V line, but the I phase, sorry, I line is actually square root I phase. Okay, so if you are using this formula here, okay, and I'm using what we call V phase. Okay, I actually substitute V phase with the V line. So this one will become V line, and I phase will become, based on this, is actually I line over square root 3 multiply with cos theta V. Okay, cos theta V. So this one I think theta V minus theta I. Okay, so from here you can see that this one is a power of 1, where the square root is actually half, the power of half. So this one will become square root 3. Okay, so V line, I line cos theta V minus theta I. Okay, and so this is proof, meaning that regardless of connection delta, okay, so you can actually also use the same formula. Okay, and let's try on Y connection. So Y connection, we are still using this formula. So you need to multiply V phase and I phase cos theta V minus theta I. Okay, and we know that for Y connection, I line is I phase. Okay, and V line is actually square root V phase. So in line term, so V phase will be square, it will be, will be V line square root 3 multiply with I phase is I line. So I line cos theta V minus theta I. So this one should be square root 3 V line I line cos theta V minus theta I. So meaning that regardless of connection type, whether it is delta on Y, so these equations are valid. So you can use this for all type of connection. Okay. We have already proved it. So that is actually, we prove for the P. The same thing is actually we can do for Q and also the apparent power. Okay. So meaning that for Q, also the value is actually same. So you have 3V phase I phase sine theta V minus theta I. You can also use the line term. Okay. And for the apparent power is 3V phase I phase, or in a line is actually square root 3V line I line. Okay. This is example 6. Okay, so for power in the balanced system, so since it is unbalanced, so meaning that you need to manually calculate each power for each phase. Okay, so it cannot be just summation of all phase. So you need to manually calculate because it is unbalanced. So manually calculate it. Okay. Okay, we have also example 7. And we go to the last subtopic here, the power measurement in a three-phase system. So actually the power that we measured is actually only the active power or real power, which is wattmeter, okay, which is P. Okay, so for the three-phase system, okay, we have two type of method in measuring the three-phase power. Okay, so we can either use what we call 2 wattmeter method, where you can see we are using only 2 wattmeter, W1 and W2. Okay, and we can also use what we call 3 wattmeter method. As you can see, we have uh, a single wattmeter installed at each phase. Okay, so which method is suitable for which system? So actually, for three-phase four-wire system, meaning that usually Y connection. Okay, so normally we are using 3 wattmeter method. Okay, and for a system, three-phase three-wire system, usually referring to what we call delta connection. So the real power can be measured by using 2 wattmeter method. Okay, is it possible? Okay, so for delta load connection, 2 or 3 wattmeter. So since actually delta, we use only actually three-phase three-wire system. So usually we are using 2 wattmeter. Okay, is it possible to use only wattmeter? When? So actually, it is possible. Yes, possible. How and when? It's actually when you sure that the system is balanced. So if the system is balanced, meaning that you can use only a single wattmeter to actually represent the power, and then you need to multiply with 3. Okay, so this is the Y connection with 4 wires. So this is Y. So as you can see, we are using 3 wattmeter method here. So this is actually how we are actually connected. And this is for the delta, okay, delta connection with 3 phase, with the 3 wires, with 3 wire here. Okay, so we can use what we call 2 wattmeter method. And we have example, which is we can actually refer to the textbook from Alexander and Sadiko. And also example 9 for wattmeter method. Okay, thank you very much. I think we finished the topic 1, okay, which is the AC power. And as you can see, we have a lot of example that we can try. Inshallah, we try to solve it during the class. Okay, and if not able to solve it, I will try to actually provide you the solution, the manual solution. Okay, so thank you very much. We meet again next time.